So you can see over there? All good?
Yeah, good.
Okay. So first of all, this is my presentation to gain my degree as an agricultural engineer from Tecnológico de Costa Rica. As you can see, the title is Developing a New Vegetation Index using Cyan, Orange, and Near-Infrared Bands to analyze soybean growth dynamics. So just to start, some information. Soybean reproductive stages are the ones that are being studied here. The whole soybean growth process consists on 10 stages, 5 vegetative stages and 5 reproductive stages, that in this case went from July 26 to September 20. For first reproductive stage, we have R4 that consists on 15 days, R5, 16 days, R6, 18 days, and R7, 7 days. And finally, R8 would be the harvest. Then, talking about the cameras and the visible light spectrum, we can see that for the light spectrum, the visible wavelengths go from 380 to 740, more or less. Then it goes to near infrared, far infrared, and it goes on to different wavelengths. But for this study, we'll just focus on the visible light spectrum range and near infrared. So for the study, two cameras were used. First, an RGN camera, which is very common on remote sensing. It includes green, red, and near infrared bands, and a new camera, the OCN, that includes cyan, orange, and near infrared. And this camera, it's quite new. So there are no vegetation indexes using these bands to express vegetation health or vegetation features. So now, just to explain a little bit what is a vegetation index, I'm going to use this example, is the NDVI. This is a widely used vegetation index. On the right, uh, down on the right, you can see the mathematical expression. It's a combination between near infrared and red wavelength. So you can see on the left side that the healthier the vegetation, the more near infrared reflectance we're going to have, and less red or less visible reflectance we're going to have. So it's possible to come up with this mathematical expression that basically the higher the NDVI, the higher or the better the vegetation health. So now talking about the study area, this is a map from the Lakehead University Agricultural Research Station where the study was held. You can see up on the left the soybean plot with two stations. Now talking about the stations, for the setups, Raspberry Pi units were used to program the cameras to take images every 30 minutes from 7 a.m. to 5 p.m. These were set up on adjustable panels. So the solar panel could be moved to use the solar position, taking into account variation during the year. And each camera had a RGN and an OCN. Sorry, each station had a RGN and an OCN camera. The station one had both cameras in a 90-degree position, and the station two had one camera on a 40-degree position and a 90-degree position. So now, talking about the objectives of the research, the specific objectives are to develop a spectral profile for soybeans growing in the ocean camera, compare the performance of different vegetation indexes at different growing seasons, and validate the performance of the new developed index using canopy leaf area index, which will be explained later in the presentation. And finally, to propose the best fitted vegetation index for cyan, orange, and near bands. So now talking about the methodology, you can see here the flow chart. So first, the data collection consists on the camera setup that I mentioned before. Each image contains a RAW and a JPEG file, and having all the images for the 4 growing stages, um, images were sorted into morning, midday, afternoon, and then if it was a sunny day, a gloomy day, or if it was a calibration target, which were used later for the pre-processing using appear control camera software. The product of this pre-processing is one raster with the 3 spectral bands having a spectral reflectance percentages. And then using RStudio, we could extract spectral values located inside leaves and different pixels for sunny midday images. Now, having all the data, for the data analysis, exploratory data analysis was applied and then outliers were removed. And now having a clear data set for each stage, it was easy to create the spectral profiles. Having the clean data sets, NDVI could be calculated and then used to calculate lever index, which is the variable used for the validation of the new index proposed later on. And some already known mathematical expressions were applied using the ocean bands. So you can see from the tested vegetation indices, um, DVI, simple ratios, NDVI and SAVI were used. And later on, having these vegetation indexes values, the correlation between these indexes and the spectral bands could be analyzed to propose new expressions. Specifically, 3 new vegetation indexes were proposed and then validated with the leaf area index, finalizing in having the best fitted index for each stage. So now, for the first objective, which was developing spectral profile for soybean, you can see here on the left the spectral profile for our forest stage. You can see cyan and orange are in similar values, and near is higher, but it's not that high. This is because the stage is very early, so chlorophyll content might be lower. You can see on the right side an image of the vegetation. You can see there are very young leaves. There's still some soil background. Then for the R5 stage, orange decreases, and near infrared has a very significant increase going up to 0.91. This is because this middle stage, R5 and also R6, are with more mature leaves, more mature plants. So near infrared goes higher. There is as I mentioned, there is a decrease in orange, but cyan remains pretty much the same. For R6, and maybe I forgot to mention, on the spectral profiles, the gray lines are spectral profiles for specific pixels, and the dark line is the mean spectral profile for the stage. So for R5, which was the previous, and this one R6, they are pretty much the same as their middle stages, mature stages. They are pretty much the same. There is high near values, constant cyan, and constant orange. Then for R7, which is a late growing stage, you can see on the right image some yellow leaves, and the gray lines on the spectral profile on the left are not as homogeneous as R5 and R6. This is because you can see that some of the leaves are already getting old. They're yellow, but there is still some green mature leaves. There is a important decrease on near infrared and an increase on orange. Now, talking about leaf area index, which was the variable used to validate the proposed index. Just for some background, leaf area index is the leaf area per ground area. So basically, the higher the leaf area index, there are going to be more sparse vegetation, we're going to see more leaves. And the way that we extracted leaf area index was using an indirect equation developed in Nebraska in 2012, where the relation between different vegetation indexes and leaf area index was studied to come up with an indirect equation. In this case, the equation used is the one on the bottom left. So it uses NDVI. It's a pretty accurate indirect equation. So that's why NDVI was calculated. Now in this graph, this is a graph for our forest stage. So for these correlations, I'm just going to present R4 and R6 because the behavior between R4 and R7 it's pretty much the same, which are the early and late stage, and the behavior between R5 and R6 are again pretty much the same, being both of them middle stages. So these correlations are between the tested vegetation indexes using the ocean bands. From all these correlations, you can see a high negative correlation um, with high statistical significance for the simple ratios of orange and cyan against NDVI using the orange band. We can see a negative correlation of 0.8 for simple ratio orange and minus 0.49 for simple ratio cyan. Then between the bands, what is important here to see is that there are no linear relationships between near infrared and cyan and orange, or between cyan and orange bands. Again, it's pretty much the same for R7. And now talking about R6, you can see that the high correlation for the simple ratios and NDVI remains high. Um, what changed here on the middle stages is the behavior between bands. You can see that again, it's mostly a non-linear relationship, but between cyan and orange, there is a linear positive relation. Now, from the previous correlation analysis, this generic equation was used to come up with the new vegetation indexes. So from the equations, you can see that um, two vegetation indexes were used, and K was used as a constant that later on became the proposed vegetation indexes. As mostly all the relationships were non-linear, um, we decided to come up with a polynomial equation. So you can see for the first vegetation index, the first and the second, it's a combination between near orange multiplied by the simple ratio of near cyan and near orange. And as a third proposed vegetation index, we have a simple ratio between cyan and orange. In here, you can see the three vegetation indexes, rasters, as an example, with a correlation value. This correlation value is the correlation between the vegetation index values and leaf area index. So the Kruskal-Wallis test initially, the Kruskal-Wallis test was applied with a 95% confidence level to make sure that there were no significant differences between leaf area index and the proposed vegetation indexes. So you can see from the values and the visible features of these images that they are accurate. For the third vegetation index on the right, we can see a higher correlation and also a higher level of details on the leaves. But for our 5, that it's a low correlation. We cannot see like very much details. This has a negative correlation because for R5, the fair index is increasing, but as you remember, the vegetation index on the right, it's a simple ratio between cyan and orange, and these values decreased for this stage. So there is a decrease on the simple ratio, but an increase on the different index. The same thing goes on for R6, which is also a middle stage. So you can see on the right side, there is a low correlation and there are no many visible features. But the first vegetation index, the combination between near orange and cyan, it presents a higher level of detail and a higher correlation. And for R7, which is a latest stage, again, the third vegetation index is the one with more visible features and higher correlation. So now, talking about the conclusions and limitations, first, we didn't have early stage data. So early stages were not being able to be studied. And the initial plan was to use chlorophyll information to come up with these vegetation indexes, but the information was lost. So we came up with a different solution for the validation, which was leaf area index. And due to lack of time, the study could not be done on a small time span like daily, so we cannot see like daily graphs. Instead, we used the stages graphs. So for the spectral profiles, the conclusion is that they behave as expected from literature of healthy vegetation spectral profile. You can see down on the left the blue, green, and red regions. And in the middle of them, we can see cyan and orange. We can see that they should remain on similar values, which is what happened on the study. There is a decrease in orange for R4 to R5. Then it remains similar, and then in the last stage, it goes up. For near infrared, there is a major increase on the middle stages. These are stages with chlorophyll and carotenoids concentrations are expected to be higher. So it will explain the high near reflectance. And cyan remain pretty much the same between all the stages. And concluding with the last specific objective, it was determined by the correlations with the leaf area index that for R5 and R6 stage, the vegetation index with the near orange and the simple ratio of near and cyan was the best one. And for R4 and R7, the simple ratio between cyan and orange. So for the presentation, that will be all. I don't know if there is any question right in the moment, or we're going to go ahead with the methodology of the presentation.
Thanks, Roger. I will just stop recording right now and